Hi everyone, this is Mr. Hall and this is a quick video about solution calculations in chemistry. This will be the first of three different videos I'm going to make because I think solution calculations are quite hard and you have to get your mind around quite a few difficult concepts. So I'll start with the unit stuff today and the basic calculations before moving on to more complex things you can do with these kind of things. So the objectives for today, there are four of them. So first off is to convert volume from centimetre to decimetre cubed, which is something you may be unfamiliar with. We're going to record the equation that lists concentration, volume and moles. We'll be able to concentrate the concentration of a solution and also round them to the correct number of significant figures. I'll try and fit that final one in, but I'll concentrate mainly on the first three. So first off, I want you to have a look at these 5 beakers. And you can see this one over here on the left-hand side is very, very pale. Whereas as you move from left to right, you can see this one is like a really, really deep red. Now, you can see that they're all the same volume, okay? So they're all kind of filled up to the brim, and there's pretty much the same gap in between them. I don't quite know how big the beakers are, probably maybe a litre, maybe, or 600 centimetres. The point is they're all the same volume, all right? However, they are different in shading because they have different amounts of red dye dissolved in it. Now, the thing that's dissolved inside it, as you may know from previous lessons, is called the solute, all right? And the water itself is the solvent. So although they've got the same amount of solvent, they've got different amounts of solute inside it. So what differs between them is the concentration, which effectively is the amount of that red solute which is dissolved inside it in the same volume, okay? So now that's one way of looking at it, but if we look at it more at sort of a particle level, it'll look a little bit like this. So this is the same picture, except I've got it slightly smaller, and we can represent these 5 beakers in this particular way. So this beaker on the left will correspond to this one corresponds to this one, and so on, and the beaker on the far right corresponds to the picture on the far right. And you can see that as you go along, there are more and more red particles dissolved in it. So on this far side, this has got more solute, okay? Whereas over here you've got less solute. But the key thing about all of them is that they have the same volume, okay? And that's really, really important. So basically, these ideas quite nicely summarize what concentration effectively is, because it's all about 2 variables. It's about the amount of stuff you've got, i.e. the volume, and it's all about the amount of solute that you have in a given solution as well. So to define concentration, this is how we basically define it. The most simple one, it's the amount of solute in a given volume of solution. Or another way of rewording it is the amount of solute per volume of solution. It doesn't really matter whether you use per or in a given. You have to kind of emphasize that it's one or the other. Now, we can be a bit more precise than that. So instead of amount of solute, chemists like working in moles. So we would say the number of moles, okay? And this number of moles replaces amount of solute. And in previous learning, you should have learned about moles. And instead of just saying in a given volume, we can say per decimeter cubed of solution. And this per decimeter cubed replaces the idea of volume there. Now you can probably see that this could form quite a nice unit actually. So the unit, it's moles per decimeter cubed, otherwise known as mole/dm3. And this is pretty much the equation that we're going to use a little bit later on. So before I go any further, let's talk about decimeters. Now decimeters is probably a measure that you're unfamiliar with. 1 decimeter is 10 centimeters. Now if I've got 1 cubic centimeter, that is 1 times 1 times 1, because if this is like a centimeter cubed cube, this would be 1 centimeter, and that would be 1 centimeter, and that would be 1 centimeter. So overall, that would be 1 centimeter cubed, okay? So if I've got 1 decimeter cubed, if I'm sticking in decimeters as my unit, and this is my big block of decimeters, it would be this, which is 1 decimeter, multiplied by this length. It's kind of hidden from view there. Let's move this out of the way for a bit. And that's 1 decimeter. If I move that back. And then this, going all the way down here, is also 1 decimeter. So it would be 1 times 1 times 1, which will give me 1 decimeter cubed. But I want to know how many centimeter cubed are in that decimeter cube. So the best way of doing that is by doing 10 times 10 times 10. And that gives me 1,000 centimeter cubed. All right. And if you look at this block, this pretty much nicely sums it up, where one of these blocks is 1 centimeter cubed. But if you've got a decimeter cubed, it's 10 by 10 by 10. Therefore, it equals to 1,000. Therefore, and this is really important, 1 decimeter cubed equals 1,000 centimeter cubed. So if you're trying to convert between centimeter cubed and decimeter cubed, this is what you have to do. To go from decimeter to centimeter, you have to multiply by 1,000, because 1 decimeter cubed equals 1,000. And to go from centimeter cubed to decimeter cubed, you have to divide by 1,000. Now this is really important for later, because we always work in decimeter cubes. So if you're ever given centimeter cubes, you always have to do that conversion. So let's do a bit of practice. If I've got 24 centimeter cubes, what's that value in decimeter cube? Now remember, going from centimeters to decimeters, I have to divide by 1,000. Therefore, for this answer, it's going to be 24 divided by 1,000, which will give me 0.024 decimeter cubed. Okay, I think that's right. However, if I've got a solution containing 0.23 decimeter cubed, you're going the other way here. So decimeter cubed to centimeter cubed is multiplying by 1,000. Therefore, I've got 0.23 multiplied by 1,000, and that equals 230 centimeter cubed. Okay, so that's the first bit. That's how you do those conversions. Let's now move on to concentration calculations. So how do we calculate concentrations? Now, if you remember what we learned about before, the number of moles of solute per decimeter cubed is our definition, and this is the one that we always have to remember. And this is our unit. Therefore, if I look at these boxes, and let's just kind of work it out logically, each red drop is equal to 1 mole, and each cube is 1 decimeter cubed. So if we think about what the concentration is in each box, well, each cube is 1 decimeter cubed. This has 1 box in 1 decimeter cubed. So that would be 1 mole per decimeter cubed. In this box, I've got 3 moles in 1 decimeter cubed. So that would be 3 moles per decimeter cubed. And here I've got 5, so it would be 5 moles per decimeter cubed. But what would happen if I made the box a lot bigger? So let's say instead of making it 1 decimeter cubed, let's say overall the volume, I expanded it massively, and it was now 8 decimeter cubed. Well, this one blob here would take up the same amount of space, but in a much bigger volume. Therefore, my concentration in this box would be 1 mole in 8 decimeter cubed, so it would be 1/8. For this box here, if it was suddenly 8 decimeter cubed as the volume, you'd have 3 moles in 8 decimeter cubed. And over in this box, you'd have 5 moles in 8 decimeter cubed. Okay. Now, this is really important, because what you're seeing is I go from left to right, my number gets bigger. And that kind of makes sense, because you've got more particles in the same volume. So, this leads us to our big equation. So the big equation is concentration equals moles divided by volume. Okay? And note, just remember that we always work in decimeter cubes, so you have to do that conversion first before doing anything else. Really, really important. So let's do a couple of examples. So this question says a 0.250 decimeter cube solution of sodium chloride contains 0.45 moles of NaCl. What is the concentration of the solution? Now, the first thing I recommend is whenever you do questions like this, write out the equation first. Now, we know that concentration equals moles divided by volume. Okay? Now, let's have a look at our question. My moles is here. I'll underline it. It's good to annotate. And that is 0.45 divided by my volume, which is 0.25. Okay? I put that in my calculator. And that gives me 1.8. Now, if you're being really fancy, you have to do it to the lowest number of significant figures based on the numbers that you were given in the question. This number is 3 significant figures. This is 2 significant figures. You have to go with the lowest for your final answer. So we're going to go with 2. If I check my answer, 1.8, that's 2 significant figures. So that works. And I'm happy with that. Remember the unit, it's moles per decimeter cubed. little bit sloppy here. I probably should have put the units there before writing two significant figures, but life goes on. Let's try another one. A 55 centimeter cubed solution of potassium iodide contains 0.685 moles of potassium iodide. What is the concentration? Now, the first thing I have to do is I've identified the volume and it's in centimeter cubed. Now remember, going from centimeter cubed to decimeter cubed is a division of 1,000. Therefore, 55 centimeter cubed divided by 1,000 should give me 0.055 decimeter cubed. Now I can work out my concentration. So concentration equals moles divided by volume, and my moles is 0.685. My volume, as I worked out here in decimeter cubed, is 0.055. Therefore, my calculation will be 0.685 over 0.055, and that gives me quite a long number, 12.4545, and basically recurring. Now, if I look at my numbers, this is two significant figures. This is three significant figures. I have to go with the lowest number, which is 2. So I have to round this to 12 moles per decimeter cubed, and I'd write in brackets 2 significant figures. Okay, and that's it. So I hope that was useful, and best of luck with your calculations on concentration.